Thank you very much. We're going to follow the same Australian rules for questions. Brian, you're first. Other people, please keep your hands up while I write your name. Brian, go ahead.
I was just wondering if you could sort of clarify the role of the preferred reference frame. Because it's understood the statement of the theorem, it could just be expressed as exceeding any fixed V light cone, which could be expressed however you like by a metric. You know, so you have a bunch of metrics corresponding to a bunch of possible physical propagators, and you have now, you know, a statement that says you exceed any given one. Is it just heuristic for the purpose of the experiment that you need a preferred reference frame, or what am I missing?
Well, I need faster than light speed. And I think faster than light speeds is difficult to define. And one simple way around that difficulty is to make the assumption of some privileged reference frame. As soon as you have some privileged reference frame, it's easy, it's a Newtonian spacetime. And then it's easy to talk about faster than light speeds. Now, if you have another way of talking about faster than light communication, influence, propagation, that would, I mean, the result would apply equally well.
So it's just for convenience of expression, really. That's what
it's more for pedagogy. I don't want to go into, you know, because I don't think everyone would agree that if I have some privileged reference frame, then I can have faster than light speeds. But if I go to strange metrics or general relativity, then I think we enter in a debate which is not the one I want to present here.
Just one question, like your result is correct, of course, but the way you present the conclusion, it seems to me that Bohmian mechanics would be a counterexample, because it's neither signaling nor is it discontinuous in the sense that you define, because they are just continuous trajectories. Matter moves in continuous trajectories all the time. It's of course a non-local law, but there's nothing discontinuous going on in nature. If you accept laws as what grounds physical explanation rather than some mechanistic picture, then you don't have the sort of problems.
So Bohm, of course, makes the assumption that the speed, maybe not Bohm himself, but at least the people who talk about Bohmian mechanics today, they all go for infinite speed. And now to say that this doesn't violate the principle of continuity is certainly not my understanding of this principle. I mean, according to this, it's like in Newton's universal gravitation theory. You change something here, it instantaneously affects everything else. I would not consider that as continuous. I would say that's typically non-continuous. It jumps from here to there. So I would say this non-continuous. Moreover, Bohmians, and I know that you are at least part of that school, claim that you cannot use Bohmian mechanics to signal, but you avoid the signaling in Bohmian mechanics only by assuming that you have no access to this hypothetical local variable, the position, the hidden position. If you could access the hidden position, you could signal. Now you say, okay, there is a signaling mechanism, but by assumption I cannot use it. And then, of course, it's no longer signaling because by assumption I cannot use the signaling mechanism. But I don't find that personally very satisfying.
Well, maybe a linguist.
I don't try to convince you. I know that this is.
You need it, but so that you cannot know the exact position is not an assumption but a theorem, so you can prove it. That's typical in quantum equilibrium mechanics. So it's a theorem, not an assumption. And you don't talk about finite, infinite speed because there's not speed must be the speed of something. There's nothing propagated.
Yeah, so you change something here and it immediately affects that. I think it's exactly as in Newton's gravitation theory. Change something here, it affects everything in the universe immediately.
It's worse than Newton because it doesn't decay with.
Sorry, even worse.
But, I mean, we know that nature is non-local, and that's a non-local law of nature. That's a story.
Yeah, okay, but so I don't think we agree about Bohm, but we should agree that this is not a contradiction with the theorem here.
I wouldn't call it discontinuous, but yeah, maybe just a linguistic.
Change the terminology.
Brian, is this on the same point, or would you like me to add you to the queue for a new point?
From the queue, yeah.
Okay, it's a fairly short queue at this point, so you won't have to wait too long. Axel,
So you were serious with this one and hand. I didn't realize.
Australians are very serious people. Echelon.
Suppose the prohibition on velocities greater than light did not exist. Do you think, Nicola, and this relates to your open questions, do you think that the EPR correlations would cease to be strange once you have no problem with the relativistic prohibition? And I would argue
With
that
relativistic?
prohibition against velocities greater than light. Suppose that you can ignore it. Would it then cease to be strange? And my argument is that it will only begin to be strange. You mentioned a few.
Well, it depends if we find. Let's suppose that this faster than light communication in privileged reference frame really exists, and someday we find it, we measure it. Then in this day we will be able to experimentally identify not only the speed v, we find a number for that speed. We also find at which speed Earth is moving with respect to this privileged reference frame, in which direction, and all that. And if we find all that, if we would find all that, that would be a perfect explanation for the seemingly non-local correlation. But they would no longer be non-local because we would have found a local explanation for them.
But then I would argue that your open questions will be many more than the ones that you listed. Let me mention.
That was only a very small subset of my open questions anyway.
Can I mention a few? Would that kind of correlation obey Newton's inverse square law? Because today we know that it does not. So then that would be a very strange kind of influence that has nothing to do with, with the distance. Wouldn't that seem to you to be a bit strange?
That would be strange. So it would not be something that, I said it goes inform all the rest of the universe. Actually, it has to inform only those particles that are entangled. So it is shooting at these particles. It's not going in all directions.
Right.
That's why it doesn't decay.
Right. And let me elaborate on that. So it's one electron between zillions of ones, and it is diverted by several mirrors, such that at the moment of your measurement, you have to know where it is. Come on, Nicola, don't you feel, don't you feel that the number of your open questions is going to increase if you just let me talk? So much that you will embrace the retrocausal model because you will say, thank you, I have this V in four dimensions and that saves me from all the trouble?
Okay. For today, at this moment in time, and only for a few minutes, I will say yes, because of the local environment.
Okay, Lev, I think you were next.
Can you specify a little more your technical result? If I understand correctly, you have a proposal that that maybe there is a finite propagation of this result. And now you say you cannot really measure it because it's difficult experimentally to do it exactly at the same time. Now you devise another experiment in which you don't need this exact timing, and you can say you can rule out any velocity of light without timing.
Yeah.
And it's not maybe it's nature. You don't think that some of the measure B. You have all these inequalities that B appear, and now you say. You start when you derive it. You have A, B, C, and D. But if B is not measured, will it be helpful? If every time when you measure only 3, not 4.
Where do I have the inequalities? Yes.
You see, it's like in CHSH. For instance, the input, let's call the inputs on any side x equals 0 and x equals 1. But the term with x equals 0 doesn't appear everywhere. It appears in some terms you have x equals 0, in some other terms for CHSH you have x equals 1. So not every term appears everywhere. Of course not. So here it's a kind of similar, but even some parties that completely disappear. So when in the first one, you only need to measure Alice here. You don't need to care about Bob, Charlie, and Dave here, because it's just Alice marginals. And okay, here you need only Alice, Charlie, and Dave, but you don't need Bob. So it's a three-party marginal here that you need.
But the time relation in this Alice, Charlie, they should correspond to this V light cone. So you need this time.
But if you don't measure, let's go back to this term here. So in this term here, you don't measure B.
Yeah, okay.
So it doesn't, It doesn't matter at what time you don't measure B. If you don't measure B, at what time you
But
do
the
not
other
measure, it
three,
doesn't make
the
sense.
other three should fulfill exact timing.
The other three must be, let's go back, okay, here, sorry. So the other three, they have to be within their V code, yes.
But, so it's
And
the
one-
same experimental difficulty.
No, because that's easy, because it's, for instance, puts Dave in the absolute future of Alice. Then if it's in the absolute future of Alice, it will also be in the V code. So it's easy, because that's not a very strict requirement to be inside the V code. The difficulty is to be outside. You don't know how open these V codes are.
So in all this, there is no any kind of V-cone in all this, in things which you measure, nothing in V-cone, and there is no requirement that B will be measured even if by somebody, even
will be measured sometime.
even if you don't measure.
But here Bob will be measured, but in this case Charlie is not measured. There is no term in which you need to measure at the same time Bob and Charlie. All the terms here are all marginal terms, and in none of these marginals you have Bob and Charlie.
My question, this was derived on the assumption that A, B, C, and D were measured by somebody. Yes? All that this is
No.
this
Why?
relation. It's
No,
true that
again,
A, B, C,
in none of these terms do you need the four parties.
This I understand, but to derive this, it was a big derivation. It started from all these things. In all these things, there is A, B, C, and D.
Yes.
Correct?
But then
If B is not measured, then probably you cannot derive this. It's something unusual. So you need that B should be measured in the right time. If it's not measured,
This is a theorem, it's not a matter of measuring. The theorem says if this is technically no signaling, so satisfies parameter independence.
so but this
And
tells about the
this
result
one
of
is
measurement,
local.
about or you believe that there are values for this, or
This is
what's the
mathematics.
status?
This is mathematics. You can forget about physics. This is a mathematical theorem. We take such a correlation function, so these numbers are between 0 and 1, they are
In
normalized.
CHS, this A, B, and X, it's parameters and measurement and outcomes.
No.
So is really you have to put parameter and you have to get outcomes, then you get your Bell inequality. So if this is like Bell inequality, the measurement has to be performed. The fact that maybe in your analysis you don't need some of them, but does not change the fact that it should be performed.
Let me
If
try.
there is some assumptions, then this quantity is smaller or equal to 7. And in this quantity, in order to evaluate this quantity, I don't need ever to measure B and C at the same time. Of course, B and C must exist, but they don't need to be measured at the same time.
We have a forest of fingers of people wanting to come in on this question. Raphael, you were the first.
Well, I was just hoping to clarify the issue, see if restating it in a slightly different way. I mean, it's in order to verify whether, or find out whether J is less than 7 or greater than 7, you need to do many, many measurements. Is that correct?
Yes, of course. Like
And
for
then in
value,
each
you do
in-
statistics. Yes.
Yes, and so in each one of them, either B or C, let's say, or in some of them B or C are measured, and they must be
In none
measured.
of them, B and C is measured.
No,
In some
that's
of
right,
them it's
that's
B,
right.
and in some of them it's C.
Correct. But when they measure, they have to be synchronized in a very precise way with the other locations
Things are
that
never
you,
measured at the same.
not with
the
each
same
other,
point,
but not
it
with
means
each other, but
synchronized.
with A and D. I mean,
Yeah,
there has to be
A,
some
B,
sort of common reference frame in which
But
all
we-
these measurements are either happening or not happening. But I think the point is that even when they do happen, they have to be very precisely synchronized, very precisely located in time.
I mean, whenever I'm measuring, let's say, this term, then I must be sure that A is in the past of D, who is itself in the past of B.
But can D move around as long as you keep those causal relations?
Because the only assumption is that B is in the future, in the V future of D, and
So
D
one,
is in the
so
V
one
future
run
of
of
A.
the,
But I thought-
one run of the experiment, you can measure A and D at one location, in another run, you can have them in another location,
As long as we
as long as you
satisfy-
keep this causal relation?
Yeah, as long as we satisfy this causal relation, yes.
I thought D was supposed to be outside the light cone of A, though, in order
Well,
to
that-
draw the
No,
conclusion that...
all what is needed is that D is inside the V cone. So one way of making D inside this V cone is to make it even, let's say, the absolute future of Alice. So you could have Alice, Dave, and then Bob and Charlie just next to each other.
And next finger, I'm sorry, I don't know them.
Just Nicola, just to clarify, so you have these various marginal quotation values. So you perform this experiment many times. But for each of these, to collect a statistic for each of these marginals, you only measure the corresponding party.
Exactly. Exactly. But that's like in Bell also, in CHSH, you do that also.
And again, I'm sorry, yes, you're the next.
So maybe it would just help to say that, like, your assumption when you're doing the quantum thing is that, like, in this setup, A, D, and B are going to follow the quantum prediction because they're B connected, right? Which means, in particular, the probabilities for A, D, and B are independent of whether C is done in the, like, B past or the B future or whatever it be. And so if you were going to do an experiment where you didn't assume quantum theory, would you not still have to make some kind of assumption that the probabilities on A, D, and B are independent of when C is measured? Because otherwise you really would have to synchronize them to be sure that...
Well, but in the experiment, again, if I measure that one, I'm not going to measure C at all. And then, okay, maybe I make the assumption, if you like, that it doesn't matter when I'm not measuring C. You know, there's not a time at which I'm not doing a measurement. I just don't measure it.
But you could imagine a theory where if you don't measure C, A, B, and D do something, but then when you do measure C, everything changes and you get completely different value for A, B, and D, right? And you are assuming that that's something.
Yeah, so I make the assumption it doesn't matter when I'm not measuring C.
Ruth.
This is really interesting, and I really understand Lev's objection, because ironically, this is the same objection that I had to some of his work on counterfactual measurements. Because what we have here is your theoretical theorem involves what we could call counterfactual measurements. Measurements that you couldn't necessarily make at all, but you have inputted those into the theorem and as entities that represent something meaningful. And Lev is objecting, and I think, rightfully so. His concern is these aren't operationally defined necessarily, although it's legitimate to use them in a mathematical theorem, but then they are these counterfactual measurements, and so that's kind of a gray area. So.
Maybe let me just remind the following. This is a mathematical result. It doesn't matter. We don't need to do an experiment to prove a theorem. We just do a mathematical proof. So the theorem holds irrespective of any experiment. Now, all these discussions that we have is how would one do experimentally to check that indeed you can violate, use quantum physics, photons to violate this inequality. But I think the result is already interesting in itself. I mean, it's the same as Bell again. Bell, I mean, there is still no loophole-free experiment, Bell test. Still, it is nevertheless an interesting result. Here there are no experiments yet on that. Still, I believe it's an interesting result.
Okay, now we're still on the same point. We're stemming I now have fingers from Lev and again from person. So Lev, you have a finger on your own point.
You have to
I ask
understand.
again, this mathematical result, you have this A, B, C, D, X, Y, Z, W. Well, what is the meaning of this? Mathematical result of what? What is the meaning of this letters? If A is the outcome of a measurement of X,
let's go just back to classical probability theory. You can have a classical probability theory with a probability distribution that you can characterize by only, you cannot really fully characterize, but you can deduce some properties of this classical probability distribution by just making assumptions on some marginals. So out of some marginals, you can deduce properties of a full probability distribution. That's what we're doing here. we only use marginals, and nevertheless we can deduce something about this full probability distribution. And this is not something new. I mean, this is well known in classical probability theory. You have plenty of examples of that sort.
But you assume that it exists.
Of course, I assume that it exists. Yes. I assume that indeed, if I would measure everything, I would get statistics. No, but that's, I mean, you have to make the assumption in physics that if you do measurements, you get results, and these results follow some statistical probability rules.
Howard, did you have also have a thing?
Perhaps it's a quick point. It seems to me that you have to have the same state in every run of your experiment, right? I mean, you're drawing from the same distribution. You're drawing from the same distribution.
No.
And so it does
No,
seem to
actually,
be like...
no. Sorry, no. It's like in Bell inequality. If I don't have each time the same state, I will not get, let's say, 2 square root of 2. I will get another number. But if I get a number which at the end is larger than 2, so I get a violation of CHSH, that's enough to conclude that I have violated Bell inequality.
Given that you...
So here it is the same. If I do my statistics, even if something is imperfect in my experiment, that for instance the state is not exactly reproducible, so it fluctuates, the measurement setting also fluctuates, as long as I get a j at the end which is strictly larger than 7, I have violated the inequality.
Right, so my main question was, do you have, so you don't have to ensure that the place where I measured B in one run and the place where I measured C in another run, which obviously B wasn't measured, you don't have to ensure that those are space-line separate.
No.
So this drawing
Because I can infer the non-locality of BC without ever measuring them simultaneously.
You can infer it. Well, it's an assumption in your theorem.
Okay, but now if I get a violation, from the violation I know that one of the two assumptions is wrong. So if I make the assumption of parameter independence, it's non-signaling, then I can conclude that BC is non-local. Or vice versa, if I'm in this V-causal model, then I can say because in this V-causal model BC are local, then necessary this correlation here, the full four-party correlation, must be signaling.
But without some control over B and C's
But I never measure them at the same time.
But without some control over them, you might not have any reason to believe that that first thing was non-signaling.
That's the same point.
I think we turn it.
What I propose to do, there are some more fingers, but what I propose to do, I think there are also some hands on the queue who've been waiting a long time. So I think I'm going to move on, and then if somebody would like to re-raise this point, when we get to the end of the queue, we can do it that way. Brian, you're the next.
Well, a couple of points. One is the question of whether consciousness might have effect if you put it in. One consideration is suppose people are connected telepathically, as in these experiments that Charlie does. Then you simply say there's some kind of rather rigid string connecting them which can transfer information very quickly. That could give you these correlations. So you're simply adding some extra mechanism to everything else.
Yeah, so I would like that this kind of telepathic connection goes at finite speed. In such a way that if people really ask questions in a well-synchronized way, they cannot use telepathy to output non-local correlations.
Well, they just be constrained, so this link would just produce a constraint without dealing with signal with it in a way. Then it might violate quantum mechanics. I guess the next point is like violation of quantum mechanics. There's paper published in Foundations of Physics about 1990, which you can access via the publications link on our web pages, where Bettina Palakari and I propose that you start from hidden variable model, and the assumption there, well, the thing that Bohm proved was when you got to some kind of equilibrium, it would reproduce the situation of quantum mechanics. Well, we argued that scientists use statistics, but organisms actually look at the details, and that the So people might work with different distributions, and then you can use the quantum potential to transmit information directly in crystals. Besides that, there were two sort of thought experiments which suggest some kind of distant connection. One is a simple one. You ask, is it a meaningful question to ask, what is my friend in New York doing at this moment? It seems that, even if we were on a different stance, that seems to be meaningful. And the other is a hypothetical situation where involving the first manned mission to Mars, and the spaceship was about to land and everyone's anxious as to whether it's okay. The astronaut's wife said, they've landed safely, I can sense it. And then 8 minutes later or whatever, the best confirmation by radio. But you see, there's nothing contradicting the idea that people can be in some instantaneous connection, but of course that does assume a privileged reference frame.
Yeah, so that's the other alternative. If you don't want to go to non-locality, you have to go to faster finite communication.
But even instantaneous. And you seem to rule that out at the beginning. But I think they can be restricted.
No, what I ruled out is communication without physical support. But then I don't know how your telepathy functions. But if there is some physical support, that's fine.
Via consciousness, yeah. Okay, well I think that's maybe wrong.
Jeremy.
Can I begin by saying that, as Shakespeare has it, I come not to bury Gisin, but to praise him. I have nothing conceptual, doubtful concerning your presentation. Just want to ask you to say more about the space of the epsilonics around the theorem and its discussion. What do we know about the quantum states for which J is greater than 7? And also, I mean, I'm completely philosophically, dialectically endorse the strategy that V causal models should be defined as having, if you're V space-like related, so that it can't arrive in time, then you can only be classically correlated or locally. Whereas if you arrive in time, then we should replicate quantum, because that's the name of the game. We're trying to put the V causal models in a corner by assuming that they're empirically adequate if their signals arrive in time. But we've got no problem about that. But I wonder whether you can do some epsilonics around this theorem, possibly by looking at the set of quantum states that have J greater than 7, so as to also reverse engineer weakening those assumptions.
Yeah, okay, thank you very much for the question. Actually, there's one thing which I forgot to say during the talk. It's written here. It's clear that you don't need to go to 4-party. Actually, we find an example with 4-party before finding an example with 3 parties. And actually, of course, there is no poster here. And this is while raising the poster, I probably also raised one of the things which I had to. This is why I had to change the file. Okay, so the other technical thing, indeed, so I told you one can violate this inequality according to quantum prediction, but you need a very bizarre quantum state, so a 4-party quantum state, or in this case a 3-party quantum state, but in both cases this state is an ugly state. So we have it explicitly, we have it with all the digits and everything, but it's not a nice state. And I don't understand why it's not a symmetric state, it's not a DHG state or anything like that. It's just a very bizarre state. Don't know why. Also, the measurement settings are not very nice. And finally, also, the violation is small, which means that the experiment will be extremely difficult because the resistance to noise will be very low. So from this point of view, the technicality here is not very promising. The experiment will be extremely difficult, require a very bizarre state, and so on. And we don't really understand it. And I have to say, we spend a lot of time trying to find a better inequality, somehow an inequality which would be easier to violate, or maybe with a nicer state, and things like that. And we have not been able to find anything nicer than that. But I don't know if it's fundamental or purely technical, as I say.
Yes.
Hi. Yeah,
just going back to your first thought experiment with the signaling. The one where the first thought experiment was the signaling, the one where Alice was a long way away and Bob and Charlie was
The triangle thing.
yeah, the triangle. So is
No, this exists only on the other slide, on the other file. No, this one.
That's the one, yeah. So is the only advantage, as you see it, of the latter experiment over this one, that in the latter one, you don't think that Bob and Charlie's need to do make their measurements in any given, say, run of the experiment in order to get out your violation? Whereas in this one, they always would have to, and so you'd have to be very precise about when they do it.
So indeed, there are two main differences. But first I should say, these are all Gedanken experiments. None of these have been done. But so in this one, indeed here we need to assume that Bob and Charlie are really not connected, not V connected. They are outside each other V cone. And here they would need to measure both of them in the same run of the experiment. So this is, as you said, one of the advantage of the later configuration with respect to that one. But the main advantage of the later one is that here, if we would add to this quantum state also some shared randomness, so some local hidden variables, it would be very easy to avoid the signaling. Because Alice, Bob, and Charlie, they all measure in this computational basis. So all measure, let's say, sigma z. And there is a very trivial hidden variable, a local hidden variable model for this state if you only measure in the computational basis.
Okay. So
the advantage of the second one is mostly to combine direct causation and common cause.
Cool. So I get the shared randomness part, that's good. But with the latter thought experiment, in order for an experiment where in every run either Bob measures or Charlie measures, in order for that to be relevant to your theorem, don't you need to assume that on those occasions where just Bob measures and those occasions where just Charlie measures, that you're still sampling from the same distribution, which is an extra assumption, which you wouldn't need if everybody measured on every run, but then you'd need this perfect synchronization. But I think this might have been what some other people were getting at earlier.
I think it's okay, you're coming back to the previous discussion, and I think that the way you put it is nice. Indeed, I make the assumption that when only, let's say, Bob is measuring, so Alice, Bob, and Dave is measuring, but not Charlie, I'm still sampling the same distribution. But so, yeah.
Does that not need to be justified?
Well, again, for me, when we say that Charlie does not measure, because I'm looking only at the marginals, I don't really see what it means to say that it would be relevant that at which time Charlie does not measure. Not even understand. I mean, I cannot go to my students and tell them now you have to precisely at that time not measure. It doesn't make any sense. You just don't measure. But understand, it's indeed, I make the assumption that I'm always sampling from the same distribution, because at the end I apply that to this P of A, B, C, D, even X, Y, Z, W.
Raphael.
Yeah, so I'm not actually going back to that discussion, but maybe this is relevant to that and some other questions. So would you agree with the following and then maybe comment on it? So what you've told us is that if there's some finite propagation velocity, but it can be much faster than light, we can communicate essentially at that velocity.
Mm-hmm. Using only classical data, classical input and output.
Only with sort of operational kind of activities. Mm-hmm. But there's a funny discontinuity here, which is if we make that speed faster, then we can communicate still faster. And if we make it even faster, we can do it even better. But if we make it infinite, then suddenly we can't communicate at all. So is that acceptable, or is it hiding that there's some experimental constraint, some parameter that's really going to infinity or going to zero, some extra precision that we need in order to achieve the higher and higher communication speed?
Yeah, I guess, yes, okay, thank you for saying that, because I didn't really think about that, but you see, B and C, they must, in order to be able to communicate faster than light, you need really, where is, oh, here it is. Yeah. You really need, in order to really now use it, so I'm not just saying about the fuel, but if you really want to communicate faster than light, then you need really to make sure that B and C are outside each other's V-cone. And if this V-cone open more and more and more, it's just, well, in the limits of infinite speed, these V-cones become flat, and there is no way for BC to be outside each other's V-cone. So there is indeed some kind of discontinuity there. Now, if this line becomes flat, horizontal, then C is necessary, well, A by C is in the past, but then B is in the future, or there's no space any longer outside each other's V-cone.
Right, and the space is actually disappearing continuously, so
The
if you
space
had to
is-
fit into it, then in some
the space
sense...
is disappearing continuously, but indeed, once it has disappeared, you can no longer use these to communicate. Indeed.
The space is not disappearing continuously because you still maintain an absolute frame of reference in which you discuss this. But the moment is infinite, then the notion of absolute frame of reference disappears. So there is really a pathology there.
Why do you say that the
Look,
previous reference
Here
frame?
here you need a sort of absolute frame of reference where you discuss about this V.
Yes.
As long as this V is finite, you really need to have the absolute frame. The moment when it's infinite, the absolute frame essentially
But why? I think, on the contrary, if I have absolute simultaneity, because it goes at infinite speed in one reference
then
frame,
it could be anything. The absolute.
I'm not sure I understand that.
We have a couple of fingers, and I think these will probably be our last questions. Ruth?
Yeah, I just wanted to add to Raphael's concern that possibly this discontinuity comes more from the meaning of communication, or what it means to signal. There's an implicit time asymmetry in it, at least insofar as someone has to be the sender of the message and someone has to be the receiver of it. And so if they are truly simultaneous, then it becomes meaningless. The very notion of communication sort of becomes meaningless. Just something to think of.
Thank you.
Oh, sure.
Suppose either Alice or Bob are moving very fast. Would that velocity that you are talking about, what kind of velocities addition would it obey? Galileo's or Einstein's?
Thank you for the question. No idea. You know, here it's
I have an
like also
idea.
with
I have an
Bell.
idea.
With Bell, you can come to a conclusion without having an explicit local hidden variable model. And here I can come to a conclusion without having an explicit V-causal model. So depending on the V-causal model, your question will be answered one way or the other. But whatever V-causal model, this result applies.
Now, is there anyone who had a hand that I missed? Anyone who hasn't had a chance to ask a question?
I hope you all have 2 hands.
Okay, in that case, please join me in thanking Nicolas for